Hi everyone, welcome to this new video. I'm going to start talking through hydrocarbons, the start of organic chemistry. So I've got a lovely image here of looks like an oil refinery, and it looks like those will be fractional distillation columns aiming to separate out, at a guess, these organic compounds that get extracted from the ground in a mixture. And some of those are what we call hydrocarbons. So that's why I chose that lovely picture. Well, kind of it. Chemistry, it's lovely, but environmentally, maybe not so much. Very lovely mountains in the background. Anyway, I'm ranting. Let's move on. Our inquiry questions for this chapter. How do we systematically name organic chemical compounds? So we're talking about naming here. And how can hydrocarbons be classified based on their structure and reactivity? So how are the atoms arranged and bonded, and how do these react? Alright, there's our syllabus dot points. Oh, what have I written down the bottom here? Back to the syllabus dot points. Again, I put them as yellow boxes where they're kind of closely fitting my notes here to kind of give you anchor points as I'm going through. My little bit of context. Let's read it. Hydrocarbons are used for a variety of purposes in everyday life, as fuels and as resources for manufacturing more complex molecules. Understanding their structures allows us, I always find my mistakes in these, allows us to predict the properties and how they may be useful to perform differing jobs such as fuels, paints, pharmaceuticals, among many others. I don't know if my English was that good in that second sentences. I'm trying to say, if we know their structures, we can predict their properties, and we can kind of predict how they'd be useful to us when we're making stuff like fuels, paints, and pharmaceuticals. So when people are making fuels and paints and pharmaceuticals, they go, oh, maybe we want a structure like this because it has this kind of properties. Or maybe we want to do a reaction where we're going to add this to that to make this new molecule, and it's going to give us these fantastic properties. Hopefully, fingers crossed, let's do it and see how it goes. Okay, first thing we need to talk about is there's an abundance of these carbon molecules here on Earth, and we can also see them out in space via spectroscopy, which we'll look at more in the next chapter. They're very, very common, and there's a huge variety of them, and we want to know what's so special about it, okay? And there's two kind of things that makes carbon so special. Number one is it's one of the most abundant elements in the universe. Now, it is kind of significant, but what I'm trying to say is it's not hugely abundant, because thinking back to the Big Bang, and not that I'm doing this from memory, I'm not that old, but knowing what we know from junior classes is the Big Bang happened, it was mostly hydrogen, a little bit of helium, touch of lithium, and all these heavy elements get forged in the stars, where the fusion goes on and on and on to make all these heavy elements. So the abundance for all these elements is kind of up and down, depending on all these nuclear reactions in stars. But carbon is one of the most abundant endpoints, or one of those most abundant reactions. So a lot of stars have been, over the life of the universe, have made a decent amount of carbon. Now, it's not a huge amount compared to the hydrogen and helium left over. And look at the x-axis on this graph. It's a logarithmic axis too. So there's still a huge amount. But out of all the elements, apart from hydrogen and helium, carbon is quite abundant. It's up there. I put that green box around there. Okay. I've also put a little bit of a reading link. If what's his name? Harold. Hide the Pain Harold. Hide the Pain Harold. If he is doing a bit of online reading there, and he looks so happy yet so in pain. If you want to read more about why carbon, there's a link. The other reason is this 4 valence electrons of carbon. It makes it able to have 4 single bonds and bond to all different types of non-metals. So it gives a variety of different structures and different shapes. So it also allows for double and triple bonds too. So it's very versatile in its bonding. It can have a lot of bonds, and it can do single and triple bonding to a variety of different nonmetals. So therefore all these combinations come together and you get literally millions of different of these carbon-based molecules. And we found them both on Earth and estimated out in space. So it's estimated that the 90% of all known molecules that we know in the universe, 90% of them are based on carbon, and carbon in it, or all its variety of bonding ways. So why they're called organic molecules is that these molecules first started to get noticed with life. So the life molecules have carbon in them. Okay, most of them, not all of them. We've since found out that there are a lot of molecules involved in life that don't necessarily have carbon in them, and they can have metals and other stuff. But those earlier molecules about what makes life work and stuff are all about carbon bonding to other stuff. And I mean, classic life molecule DNA, a lot of carbon molecules in there as long as with its phosphate background. So it's about those carbon molecules that are giving us this variety of different molecules that have very different properties. So that's why it's called organic chemistry. Doesn't mean it's good. Don't relate it to the hippie organic word. Oh, it's organic tomatoes. Anyway, that's a separate rant. I'll shut up there. So I've put some images in here of carbon bonding in different ways. So there's carbon-Lewis structure up the top. We've got carbon tetrachloride, carbon single bonding with 4 chlorines. We've got a double bond there with oxygen. We've got ethane, ethene, ethine, which we're going to learn about more later. So single, double, triple bond there. We've got this ring-like structure that's called benzene. And we've got multiple ring-like structures and all this crazy stuff happening, like complex life stuff. So it gets quite complex is the word. That's good. Good word there. So covalent bonding in carbon. Okay, this is just a little revision on molecule shape way back from last year. Remember Vesper theory and stuff like that. So when carbon has 4 single bonds, it has 4 bonds equally arranged from each other. It's going to be this tetrahedral shape. Each is going to be 109.5 degrees away from each other, and our example is methane. We'll get to that soon. When you have 1 double and 2 single bonds, you have 3 bonding regions, and each of those will push away at each other equally. So it's going to be in a single plane at 120 degrees between each of these bonds. 120, 120, 120, all in the same plane. Well, you have 2 bonding regions, or 2 double bonds, or even 2 bonding regions, 1 single bond and a triple bond. They're both going to form linear molecules where those regions of electrons are going to be 180 degrees away from each other. So let's look at our example of our molecular shape here. With ethane, this molecule here, each carbon center is going to be tetrahedrally shaped away from each other. With this ethane center, 2 there, they're going to be 120 degrees away from each other. So that makes the whole molecule planar and 120 degrees between each of these bonds. Ethine here has 2 bonding regions around each of these carbons, so it's going to be a totally linear molecule. Triple bond in the middle. So we need to think about the shape of these molecules too. Okay, let's do some examples together. Lewis dot diagram of methane. I'm doing this and going back because a few people were like, oh, Lewis dot diagrams, that was so long ago. So I just thought I'd chuck this in as a revision. Carbon has 4 valence electrons. Look at the periodic table, count the amount of electrons from the left-hand side. How many in its valence shell? 1, 2, 3, 4. Let's evenly distribute. 1, 2, 3, 4. Hydrogen has 1 valence electron. Okay, and the formula has said that there's 4. Let's evenly space them around there. Okay, what's going to happen is these electrons are going to start sharing and coming into the region between them, drawing arrows into the region, and they're going to share and fill and make a covalent bond. So let me draw the molecule to the right. We're going to have carbon, single bond, to hydrogen, and single bond, single bond, single bond. Okay, now let's check that each atom has its required filled valence shell. Our carbon in the middle has 2 electrons from each of these single bonds. So it has 4 single bonds, so it has its 8 electrons all tied up in those 4 bonds. So it's got its octet, it's happy. Remember that hydrogen doesn't need an octet, it just needs 2 electrons to fill its 1s orbital. It's got the 2 electrons that are in that single bond, so each of those 4 electrons is happy, stable with its 2 electrons. So our molecule here that we've got is that shape there, or I shouldn't say shape, that form there. Why not let's go talk about shape. How many bonding regions have we got? We've got 1, 2, 3, 4, and they're 4 single bonds. They're equally going to be arranged around a 3D sphere. We're going to form a tetrahedral shape. Going to dash and wedge it because it's 3-dimensional. Okay, those 3 are in the plane, but there must be one coming out at us, one that's in our face, and one that's hiding behind the screen. So it has our dash. So methane is tetrahedral. Okay, Lewis dot diagram of carbon dioxide. A little bit of revision. Carbon 1, 2, 3, 4. 1 oxygen here. It has 6 valence electrons. Okay, let's draw and form single bonds. This electron comes in. This electron comes in. This electron comes in. This electron comes in to fill the gap there. Let's redraw and see what's happening. Okay, this carbon in the middle has 2 bonds in each, 2 electrons in each bond, so that's 4, and then 5 and 6. It hasn't got its full octet. Each oxygen has 2 in each bond, and then 4, 6, 7. It hasn't got its full octet, and it needs an octet. What's going to happen? It's going to share some more electrons. Oh, help if I didn't use arrays. That electron that was there is coming in there. That one will go in there. That one will go in there. That one will go in there. And we're going to start forming double bonds. Okay, let's redraw our molecule just below. Okay, the 2 lone pairs on each oxygen left over. The carbon in the middle has 2 double bonds, 4 electrons in each of those, so that's 8 electrons taken care of. Each oxygen has a double bond, so that's 4 electrons, and then 2 lone pairs, which is 8 electrons. So this structure here is our final structure for carbon dioxide. Now, while we're here, let's consider the shape. How many bonding regions? 1, 2 around that central carbon. So it must be a linear molecule, kind of like what I've drawn it there. It's a linear, 180 degrees apart around that central carbon. Linear. Okay. Carbon monoxide. Oh, I think I have trouble with this one all the time. I'm going to skip that one. Yeah, I'm not going to embarrass myself. Draw the Lewis dot diagram for ethine. Oh, look at this one. Carbon, carbon. 1, 2, 3, 4. 1, 2, 3, 4. And there's 2 hydrogens. Notice I'm putting the hydrogens on the outside. Hydrogens only want to form 1 single bond. Okay, so therefore a hydrogen can't be in between the 2 carbons because it can't have 2 bonds. So it must be the carbon and carbon must be forming at least a single bond between them. So let's form a single bond there, and let's form a single bond here, and let's see what we get. Carbon, single bond to the hydrogen, and we've got 1, 2, 3, 4. Okay, hydrogens are happy. They've got its 2 1s orbital electrons in that single bond, but each carbon there has got 2, 4, 5, 6 electrons. It's not happy. It's going to want to share some more. Let's put some more in between them. Let's put that one and that one to make a double bond in there. Okay, Carbon double bonded carbon, hydrogen, hydrogen. We've got one electron left over on each carbon. Should be getting the picture that that's not very likely. Each carbon now has 2, 4, 4 in the double bond, extra 2 on the single bond, so that's 6, and then it's single electron, 7. You can see that that's not adding up to 8. It's going to share those last 2. Also, carbon doesn't like lone pairs. I think that's what tripped me up. Oh yeah, that's what trips me up with carbon monoxide. I'll go back and do that one, because there is a lone pair on that one, but usually there's not. Anyway, I get distracted, don't I? So we've got a triple bond, hydrogen, hydrogen. So each carbon there has, it's 6 in that triple bond and 2 in the single bond. So each atom there, or each of the carbons has its octet, and each of the hydrogen has its doublet. It's 2 that belong in the 1s orbital. So there's the dot diagram of ethine, and because each carbon has 2 bonding regions around it, the single bond and the triple bond, it's actually a linear molecule. Linear, if I can spell. Okay, now I'm going to go back, and now that I remember that lone pair on the carbon, I'm going to do it here with the carbon monoxide. Let's do our 4 on carbon. Oxygen has 6 valence electrons from the periodic table. Counting from the left. Okay. Let's start sharing. Let's share at least 1. Form a single bond. That's where you start out. It's always good. How much we got left? 1, 2, 3. And 1, 2, 3. Okay. Each doesn't have its octet. Obviously, it's going to share some more. Okay, let's put a double bond in between. That's what we're saying. Okay. 2 lone pairs there and a lone pair on the carbon. Okay. So, carbon. Oh, have I done it right? I've just hit a brain fart. Carbon has its 2, 4 in the double bond, and then 6 with its lone pair. Oh, hasn't got its octet. Oxygen, in the meantime, has its 2 lone pairs, which is 4, and its double bond, which is 8. Okay, what's going to happen is, to make the carbon have its octet, these 2 are going to come in and form a triple bond. Okay, so now carbon has a triple bond with oxygen. It has 1 lone pair. The carbon has its lone pair. So each has the 6 shared and its lone pair. So there's its octet. And because there's only 2 atoms in the molecule, it must be linear. You don't have a central atom there. I remember carbon monoxide. I went back. Oh, no good. All right. I'm going to talk a little bit more, a little bit longer. So a hydrocarbon, when we're using that term, it refers to any molecule that only contains carbon and hydrogen in any combination there, but it just has carbon and hydrogen. Okay, that can happen in so many different ways because of the versatility in the bonding between carbon and itself and hydrogen. Okay, so they can be really, really long chains. They can have double bonds. They can have triple bonds. They can make a ring. They can be branched. So because of all these different combinations and different possibilities, we need a rigorous naming scheme in order to distinguish between them. Okay, and so what happened was, when they all started to discover, they're like, oh, we need a naming scheme. We're going to start with this kind of idea. And as more and more of these molecules got discovered, that kind of naming system kind of got adapted until it was at the breaking point and it couldn't really do a good job. So the chemistry wizards, the IUPAC Council, who also name new elements, they came together and did a new naming system. It makes it a lot easier, but you can still see with the variety of different molecules that it does have problems. But we'll start with the basics and simple stuff in this chapter. Okay, another property of these hydrocarbons is, the first one we can look at is the term saturated or unsaturated. Saturated hydrocarbons consist of entirely single bonds. So think of the molecule has single bonds between each carbon, and the rest of the bonding around, so each carbon has 4 bonds, it must be entirely full of hydrogens, or it's saturated with hydrogens. So because any carbon or hydrogen must be a single bond, because hydrogen doesn't want any more electrons, it must be that all carbon-carbon bonds are single in saturated molecules. So therefore, unsaturated molecules have at least one double or triple carbon bond. Okay, so examples in the diagram here, on the left-hand side, we've got a saturated molecule because single bonds between those carbons. And here, further to the right, we've got an unsaturated because we've got a double bond in between those two carbons. Now, we start to get different terms that we come across, like polyunsaturated and monounsaturated and all this crazy stuff in here. Let's go a little bit deeper. Polyunsaturated means that it's just got more than one double or triple bond in there. So technically, it's still unsaturated, but if you want to be a bit more specific and a bit more pedantic, they call it polyunsaturated. Poly meaning many. We use poly as a prefix to mean many. So many unsaturations. So muggles, or non-chemistry folk, use the term when referring to different fats. So you might have heard of it around there. Fats are just very long chain organic molecules with some oxygen stuff happening at one end. So a little bit of history, it was widely believed throughout the 20th century, and especially the late 20th century, that saturated fats, or long chain molecules with only single carbon to carbon bonds in them, were bad to eat, and they're going to give you cholesterol and you're going to get heart disease and stuff. So the alternative was to use polyunsaturated fats, not fates, terrible, and they were considered the good fats. This is in the late 20th century when I was younger, because I'm old, and so they didn't cause heart disease as much. So, and anyway, 40 years of science is happening, and it's more complicated than that, but this saturated fat and all this crazy stuff is gone out of fashion, and it's not true, and really just eat in moderation, guys. But anyway, that's where you hear the term, some people are still using polyunsaturated and saturated fats were all bad. The ideas still stick around with muggles. So that's where you may have come across it. So here's a nice diagram that I found somewhere online about a table unsaturated to saturated. Not all of these will be helpful now, but it'll be a good revision thing to go on with there. Okay, another property is we can get the carbons forming a ring, and we call that a cyclic hydrocarbon. So a cyclic hydrocarbon contains a chain of carbons in a loop that comes back to itself. Like here with cyclobutane, we've got a loop of 4, and cyclopentane, we've got a loop of 5. So you need to form a loop. You can't form a loop with 2 atoms, so the smallest one's going to be 3 atoms, and they can get bigger. Okay, there's a limit too, though. So they may contain other atoms in their carbon chain. So you can also have cyclic organic molecules, not just cyclic hydrocarbons. And sometimes you do get stuff like, I've given an example of glucose, you've got oxygen in the ring and stuff like that. And here you've got nitrogen in the ring with adenine. Adenine is the A in the DNAs, the CGTA. That A is the adenine molecule, so this molecule here. But I've just given you that because it contains nitrogen in there. Just an example, don't memorize it. Acyclic, remember the A prefix usually just means not. So here, acyclic molecules do not contain a cycle. So we don't use that term very often, but cyclic, acyclic. Okay. Let's start to talk about how we represent these structures and how I've kind of been doing it already. There's a variety of different ways. So we can represent them very simply, the shortest way, by a molecular formula. Remember, a molecular formula just lists the atom present in the molecule and the number of them. And it only lists each type of atom once. So here, carbon, hydrogen, and oxygen are in the molecule. They're only listed once, and it gives you the total number of them. That's the simplest way, okay? After that, you've got an expanded formula, which is still using the symbols, but it tries to hint at some structure of this molecule. So remember when we were talking about ethanoic acid and we listed it as CH3COOH, we didn't put the carbons together. What we tried to hint at is some structure. We tried to hint at some structure by showing that the carbon is over here. We tried to hint at some structure. So without that structure in there, the CH3COOH, we could also write it as, oh yeah, I've done it in an example, C2H4O2. But from the C2H4O2, we don't get much information on bonding. We know what's there and how many, but the CH3COOH tells us a little bit more information, okay, about how it's bonded. Because we can have things called isomers. They can have the same molecular formula, but be arranged differently. And we'll get much more in depth in here, just introducing the concept here. The molecular formula C2H4O2, you can arrange these in two different ways. We have one called ethanoic acid. Here is its structure. I've drawn it all out, and it has a formula C2H4O2, or you can put them in any order. We got an expanded formula CH3COOH, CH3COOH. It's showing some structure there. But we also have propan-1-ol. It also... Oh, I've given a different example. It's not an isomer. It doesn't have the same. So what we can do is hint at some structure with expanded formulas. So this has a formula C3H8O. Sorry, it's not an isomer. I'll get to that soon. But it is arranged in a different way and has a different number. But we can represent some of the structure to it by putting the CH... Well, that should be... So the CH2OH is this bit, and then the CH2 is this bit, and the CH3 is that bit. So we can show a bit of the structure in the expanded formula. So a molecular formula is the most efficient and succinct way. It helps to lessen mistakes when calculating molar masses. Yeah, you can see how that's going to happen because you're only considering one atom at each time. And it's important because some analysis methods, some methods where we find out what's in molecules, are only able to identify what atoms are there and the numbers. So they can only give us a molecular formula. They can't tell us how it's bonded together. So some analytical methods where we use an instrument to find out what's in a molecule can only give us this molecular formula. So for an example, if an analysis gives the formula of C3H8O, there's three different ways that these atoms can be arranged. We don't know which one it is. So there's three different ways that you can form C3H8O. You've got this molecule here, this molecule here, and this molecule here. All of them have the same molecular formula, but each are quite different molecules which will have different properties. But they have the same number of atoms and the same type of atoms, just bonded differently. And these are called isomers, which I'll get to soon. So a molecular formula can be ambiguous, especially as molecules get larger. More atoms equals more different ways to arrange them. So we need good naming and a good way to draw these. Two more slides and then I'll call it quits. Okay, so structures. So we can represent the structures of these molecules in different ways, and here's three different ways that the textbooks is given. This way is the ball and stick way. You can see why. Each atom is a ball and each bond is a stick. Okay, the one in between there is, what did I name it? The structural formula. And that's kind of what I've been using earlier. So each atom is represented by the symbol for it, and each covalent bond is a line in between it. Okay, and you also got the space filling model, this last one here. Very similar to ball and stick, but they get rid of the stick. Okay, they try to show that the electron orbitals are overlapping in our model, which is true, rather than there's a gap between them and there's a stick there. It's hard to tell with bonds though. You can't tell between double and triple bonds, see. You got to guess. So look at this one called ethene, here you can see, oh, there's two to make a double bond, two to make a double bond, but that's base filling. Oh, you're going to have to know a bit more and delve in depth to go, oh, that must be a double bond in there. So 3 different ways to represent structures: ball and stick, structural formula, and space filling. I'll tend to, and most people by hand, and in exams you'll tend to stick to the structural formula there. You can't imagine you being asked to be drawing a ball and stick, but ball and stick models do help when representing 3D structures. Really good at that. Okay. Another good way that you can produce ball and stick models at home and for assignments is to use this website called Moleview. I use it to make all these structures in my notes as well. So you can put in a search name in there and it brings up the molecule, or you can use some tools around here to alter the molecule too, and it makes a 3D representation that you can click and drag around too and see it in 3D shapes. It's a really good little app there. Alright, I'm going to finish with this one, and the next one will start being examples. So the structural formula is really good. There's some limitations to it. It doesn't show 3D shapes and stuff, and we need to do dashes and wedges. But there's some different ways that we can even use structural formula. This one here is called fully expanded. It's kind of what we tend to use in this course. It shows all the hydrogens in there. It's really good. Limitations are that those angles aren't 90 though. You can do dash or wedges. It takes an awful long time. Once you're really getting more into practice with this, you're going to reach a point where you're frustrated and going, oh, I'm sick of drawing in hydrogens. One way that people have saved time to do this is they've done a condensed formula. So this is the same molecule as the one on the left, it's just condensed. Notice how this group up here, the CH3, they've just written the carbon and the hydrogens together. And here they've put them together. And so around each carbon, they've put the hydrogens associated just to save a bit of time. Okay, so that's called a condensed formula. You can go a bit more. We don't tend to do it in this course, but I'll do it occasionally and throw it in there, and we'll consider a few. And it's called the skeletal structure. So it's the bare bones. And what we do here is we only show the bonds between carbon to carbon or carbon to any other atom. We don't show any hydrogens. So this is the same molecule, but it's just showing the carbon to carbon bonds. So if we look at the backbone here, it's got 1, 2, 3, 4, 5, 6 carbons. And here, single to single, here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 carbons are there. So where those bonds meet is a carbon. Where those bonds meet is a carbon. So it's only showing the bonds in there, this line. Okay, and you can see that there's 2 carbons coming off here, 2 carbons coming off here, and 1 carbon coming off there, 1 carbon coming off there. Where it hasn't shown any bonds, it's not showing the carbon to hydrogen bonds. So me as a chemist, I look at the structural one and go, oh, there's a carbon here, but there's no other bonds, so there must also be 3 other hydrogens bonded there. And I can deduce that formula there. It saves a lot of time. It takes a lot of skill to get there though. Don't start doing skeletal structures at this stage, but if you have a lot of practice and you feel confident and you get sick of doing condensed and expanded formulas, maybe by the HSC you'll reach a point to get to skeletal. Don't push yourself though. And I'd recommend doing an expanded formula in the HSC. Take the time in your test and don't get it wrong. It's much easier to get a skeletal structure wrong and make a fool of yourself in a test. Alright, I've given you a little link there if you want more information on skeletal, I think. I'll leave the video there. That's enough of me ranting. Thanks for listening.